Hi, my name is Mira. Within the next few minutes, I'll give you some insights about how AVL FIRE M can help you developing electric machines. FIRE M is a 3D CFD simulation software developed by AVL. Our e-motor simulation capabilities help managing the thermal load of e-motors based on optimized cooling concepts. Let's look at it a little bit more in detail. A dedicated analysis workflow is integrated in FIRE M to handle the task. It leads its user from managing input data, such as 3D CAD models, all the way to reporting simulation results. The workflow integrates all critical physics, including temperature-dependent material properties, anisotropic laminations, and contact resistances. This ensures accurate thermal predictions for real-world conditions. It also allows calculating, or if already known, importing electromagnetic losses, including electric, magnetic, hysteresis, and eddy current losses. These are key inputs for the thermal analysis of e-motors and ensure a precise heat source mapping. Conjugate heat transfer modeling combines fluid and solid domains in one simulation. Modeling of all cooling approaches is supported. Also, both steady-state and transient conditions can be analyzed. This provides results of highest accuracy for all e-motor cooling variants. The complete workflow is represented in the FIRE M E-Motor cooling app. This app is a unique solution. It automates the key steps in the workflow, thus minimizing the effort for modeling, execution, and result analysis. This makes simulation accessible to people who usually feel at home more in the real world, but also simulation experts greatly benefit from reduced manual efforts and analysis turnaround time. In a first step, the CAD data describing the e-motor to be analyzed are optimally processed, so to support subsequent mesh generation. The discretization of the computational domain is then performed automatically. The resulting mesh will feature an appropriate resolution to resolve geometrical details and the physics you're interested in. The user of the app barely needs to interact with the software to accomplish all this. The setup of the analysis task is automated too, based on best practice simulation models as well as the values of numerical and physical model parameters are pre-selected. Material data are accessible through an extensive database. The app also automatically extracts the key thermal performance indicators from the simulation results and creates, if desired, a PowerPoint-based report. The results are provided in such a way as to facilitate further decision-making. The e-motor cooling app offers clear advantages. Its users can easily and quickly perform thermal analysis of electric motors in a structured and reproducible manner and obtain high-quality results. And here's the app in action. Just watch the subtitled video to see how it works and what it does. Launch the e-motor cooling app. Select geometry and define cooling concept. Map geometry parts to simulation components. This information is key for the process and used through the workflow. Press Analyze the e-motor geometry. Refinement zones created at injector locations. Optimal polymesher setup is derived. Press Create Simulation Model. Simulation setup, all inputs pre-filled. Domains, materials, boundary conditions, and more are auto-assigned. AVL expertise built into every step. User only defines physical values. one-click engineering report generation, automated PowerPoint and post-processing project, preview of PowerPoint pages and key thermal KPIs. FIRE M predicts fluid and structure temperatures for all cooling concepts. Here are examples for water and air-cooled motors. FIRE M calculated the heat transfer between coolant and structure and provides the temperature of the solid parts. Added to the slide is now an example for an oil spay-cooled motor. With FIRE M, the oil distribution, the size of the wetted surface, the heat transfer between oil and structure parts, and eventually, again, the temperature of the motor parts is calculated. I guess you are interested in knowing how well FIRE M can predict the thermal load of an e-motor. Let's figure it out. On the left of the slide, you can see an example of an oil spray-cooled motor with very good agreement between measured and calculated temperatures for different locations at the front and rear end windings. In the center of the slide, you see now a comparison of calculated and measured temperatures for a transient test cycle of an e-motor. Also, in this case, FIRE M provides results that excellently agree to the measured data. On the right are now shown once more results obtained for an e-motor with a cooling jacket. Also for this case, in all regions, front and rear end windings, as well as in the stator, the simulation results nicely match the measured data. Looking at these three representative examples, we can summarize that FIRE M predictions typically match measurements within ±5 Kelvin. This is true for both steady-state and transient duty cycles. FIRE M not only enables analysis of specific configurations, but is made for design optimization. Inputs can be easily parameterized, and variations are executed in case studies. In this example, 4 e-motor cooling concepts were compared to find the one that provides the highest oil wetting area and the lowest winding temperature. The figures on the bottom right compare the calculated oil distribution for the given designs. Now the resulting winding temperature distribution is shown for each design. Design 4 turns out to improve the cooling of the windings by 40%. This is a good example of how simulations enable safe design decisions. Simulation captures the complexity engineers face when developing e-motors, for example, oil wetting, hotspots, and transient behavior. Better than physical testing, it provides full 3D insights, while measurements typically provide data only for selected spots. Our simulations demonstrable accelerate e-motor thermal development and significantly reduce testing efforts. This means not only saving time, but also saving money. FIRE M simulations are based on validated models and methodologies. This supports informed decisions at an early stage of the development, and thus helps to find the best solution with minimal resource expenditure. With this, I'd like to thank you for your time and your attention. I'd be happy to meet you again for an in-depth discussions on topics related to e-motor thermal analysis or other topics you are interested in.